Sorry, I had not put on the microphone. Right, is the slide visible? Remote position control system?
Yes, ma'am. Yes, ma'am.
Okay, yes, ma'am. Okay. So basically over here today, what we are going to do is we are going to do an application of control systems. Now, if people come on turning in late, it's going to disrupt the class. Maybe I'll admit one or two more, but not after that. Anyway, so over here, we are going to do an application of some of the control systems components that we've already studied, as well as some other things that have to be added so that we get a remote position control system. So I think, I hope the animation is visible. Animation means not much of an animation. You can see the radar antenna on the right side with the green background. That one is turning in this direction and the other, right? And basically, what we are, about to study is the application is related to positioning of a dish or antenna in the direction of a target, right? And that is going to be done, in a remote fashion. So that is why this system is called a remote position control system. I'll get to the details as we go by. So as you can see, this left-hand side topmost diagram, there is a dish. Now let us assume that, I hope the cursor is visible. Let us assume that there is a target somewhere in the skies, right? So if it is a moving target, then the requirement is that this dish has to be, the position of the dish has to be, angular position has to be such that it is pointing towards the target, right? So if the target is a stationary one, the dish has to be positioned once and for all in that angular orientation. However, if the target is moving, then the position of the dish should accordingly, the angular position, should accordingly be changing. So that is what, this animation is trying to show you. Not a very good one, but anyway, that is all I could lay my hands on. It's just taken down from some website. I don't remember, but anyway. So the dish would be moving in, the direction of the target. Now, even if the target is stationary, then also it may so happen that there are some disturbances which are disorienting the angular orientation of the antenna. And as a result of that, again, the antenna has to be properly positioned. So the remote position control system will do that job. That is the job of pointing the dish towards the target, right? So what you see over here at the bottom is a schematic diagram of the system that we are about to study, which will do the task that we have discussed. I'll come to the details of the notations, and also, of course, we will finally get to the model, that is, we will derive the transfer function for this particular remote position control system. But before that now, okay, so we are going to actually okay, possibly the last person I can admit before I finish off with this one. Okay, so here you can see the remote position control system schematic diagram drawn. I will not actually call it a block diagram because you can see some of the components are actually there while others are schematically shown with dotted lines and all that. I describe that, and as well as describe the notations which are actually used over here to denote the different parameters of this system. So we'll go one by one. The photograph over here is the same one that you saw on the previous slide, just showing that basically this system that we are about to study is, physically going to have an appearance which looks like this, right? So one by one, we are going to define the parameters first. Parameters or the signals, that is the variable names. So first of all, we have theta suffix r, that is this one. I hope you can see my cursor. So this is theta r, that is the angular displacement of the reference input shaft in radians. So basically, you can see over here, first of all, let me, just, overall, they give you a brief overview rather of the diagram, and then I'll go to the notations. So here you can see certain things. First of all, here, this unit over here, you can see is, what is this unit? We've already studied this. what is this unit over here? It is a potentiometric error detector, right? So potentiometric error detector which is constructed by using a potentiometer. And as it is a schematic diagram, you can see basically we are going to deal with angular positions, but I mean, it is shown in a linear fashion, meaning that it's, drawn like this as a straight line element. The element is shown as a straight line, whereas actually, if I would have actually wanted to express it in a bit more detailed fashion, as far as the construction is concerned, in that case, I would have had to draw a circular element over here as well as over there. But here it is implied, right? So both these elements are going to be circular because theta r, that is angular displacement, is what is of interest to us, right? So since this is a potentiometric error detector, you find that there are 2 pointers. One that is coming from the reference shaft, that is shown with the dotted line over here. And the corresponding angle is theta r, which is the angular displacement of the reference or input shaft, right? The other pointer you can see over here is actually coupled to the load shaft. Basically, this side is this unit over here is the load. You can see the JL and FL, and the shaft of the motor is connected via a gear train to the shaft of the load. So this basically is the coupling shown with dotted lines. So theta C is the output angular displacement, right? So, okay, so let us come to that. So angular displacement of the output shaft in radians is theta C. So together now, in the potentiometric error detector, the output of the potentiometric error detector is denoted as epsilon over here. I'll come to the notations. But this epsilon is going to give me a difference between the 2 angular displacements, namely the reference input angular displacement as well as the load angular displacement. The difference is going to generate a proportional output voltage. So, your epsilon will be proportional to the difference between theta r and theta c. And you can see that the error sensitivity is denoted by Ke. I'll come to the notations and the units in a moment, one by one. So, this unit, as I already mentioned, is the potentiometric error detector. Now, the output of the potentiometric error detector is going to an amplifier over here with the gain Ka. And the amplifier is applying voltage Va across the armature of a motor over here. And here you can see the configuration. Basically, the field is shown, the armature is shown, and then the armature shaft, armature is coupled via mechanical coupling and via a gear train over here to the load shaft. And as I've already mentioned, the load shaft is mechanically coupled to the input side. So that actually amounts for the feedback signal. So now I'll, sort of describe the notations and then again come back to this system. The overview of the system. So now, theta suffix L is the angular displacement of the load shaft. So basically, this is the load. Theta L is the angular displacement of the load shaft. And theta C was the angular displacement of the output shaft. Output shaft means over here, of course, this is connected via a gear train. And theta L and theta C are basically the same quantity. Now, it may have been that there was another gear train over here, so that theta C and theta L are not essentially equal. Over here, what has been shown is that theta C is equal to theta L because, this mechanical coupling is directly done with the load shaft. But if the coupling would have been done through gearing arrangement over here, in that case, there would have been a ratio, a conversion ratio between theta C and theta L. However, for this particular setup that we are showing over here, theta C is equal to theta L. Now, theta M, you can see theta M over here is the angular displacement of the motor shaft. So angular displacement of the motor shaft you can see over here, and you can also see that the motor shaft is connected via this gearing arrangement over here. Gear train ratio is given, and then that is coupled to the load shaft. So basically, if the gear train was such that the gear ratio was 1:1, then theta m and theta l would have been the same. But here it is not the same. It is going to be, the conversion factor would have to be taken into account. Now coming to the this error detector, right? So KE is the gain of the potentiometric error detector. So it is also known as the sensitivity of the error detector, KE. Now, what would be the units of KE? It's already given over there, but nevertheless, we can also understand what would be the gain, because the output of the potentiometric error detector is a voltage, isn't it? Because it's being, we've already studied this. Output of potentiometric error detector would be voltage proportional to the difference in the angular orientations. So output is voltage, input is angle, right? Angular displacement. So angular displacement could either be in degrees or in radians. If we consider the angular displacements, say theta r, theta c, we've said are in radians. So in that case, KE unit will be volt per radian. If theta r and theta c and theta l, etc., were in degrees, then KE would have been in volts per degrees. So KE is the gain of the potentiometric error detector, also known as the sensitivity of the error detector that we've already studied. Now, the amplifier, that is this unit over here. We can see that the output of the potentiometric error detector, denoted by epsilon, is being applied at the input of this amplifier, and the output of the amplifier is being connected to the motor unit over here. So KA is the gain of the potentiometric error of the amplifier. So gain of the amplifier, output is KA. The output is gain. I'll reframe that sentence. The gain of the potentiometric gain of the amplifier is KA. Let me show this. Gain of the amplifier is KA. Output is in volts. Input is in volts. So that is why it is unitless, or rather we've said that the gain is going to be in volts per volt, implying that the output is in volt, input is also volt over here, right? So the gain is simple. It's a simple constant, KA. And if, you consider the units of the output and input, both are in volts. So that is why it is mentioned like this. Next is VA. So VA is the armature voltage that is actually coming from the output of the amplifier. And now here you find that this is what is this over here? It is a motor unit, right? So this motor is basically, you see, the supply is being applied at the armature side while the field current is kept constant. So what is the nature of this? What sort of motor are we using over here? We are using you can see it's a DC motor because I put the brushes over there and the notation also is, matching. So it is a DC servo motor, which is armature control. So an armature control DC servo motor is what we have over here. We can see the field current is constant and VA is being applied from the output of the amplifier. That is, VA is the armature voltage, the voltage which is applied to the armature, right? So you can see the other end of the armature is grounded, and also the armature resistance and inductance, I think we are going to describe separately. There is a mismatch in the notation over here. I keep on forgetting to change that year after year. Basically, the small array that I've mentioned over here is what is the armature winding resistance in ohms. Okay, ignore the capital R over here. It's the same thing I mean. Okay, so RA is the armature winding resistance in ohms, and now LA is the IA I've taken first. IA is the armature winding current in amperes. So you can see IA indicated by an arrow, the direction, and that is the armature winding current in amperes. LA is the armature winding inductance. So this is the armature winding inductance. LA would be negligible. So we will be considering that LA is negligible when we do the analysis. next, we define the notation for the back EMF. That is taken as E suffix B. It's not written on the diagram, but I mean the notation is EB, which is the back EMF in volts, which would be required in any case while deriving the model. And KB being the back EMF constant, which is volts per radians per second, which amounts to volt second per radian, right? And then, of course, for the load side, the moment of inertia of the load in kg meter square is JL. You can see that. And the viscous friction coefficient of the load is Newton meter per radian per second, which is Newton meter second per radian. So that is FL shown over here in the diagram. I hope you can see the cursor. Otherwise, you will fall asleep. You will not be able to follow. Let me know if you can't. Okay. So Km now is the motor torque constant in Newton meter per volt. So when we use the model of the motor directly, we would be requiring these constants and parameters as well. Now, as far as the motor is concerned, Jm is the moment of inertia of the motor in kg meter square. Fm is the viscous friction coefficient of the motor. That is negligible, right? So those are basically the notations which are used. You can also see Ki over here. If we require it, we'll be using it with the proper units, of course, right? So now, just to show you that, such a remote position control system may also be used in the case of, in a ship, right? So over here in the ship, what you find is that there will be, on the deck itself, some antennas may be positioned. And now, what is the, of course, okay. So in this diagram, you find, okay, these are the dishes. Now, depending on the direction of the target, basically, there will be a person who is operating the directional orientation of the dish antenna, but he will not be actually standing on the deck and doing it. What they will be doing is that there will be a sort of control room, which is shown over here. You can see this fellow. And by, say, for example, by using a dial or a steer ring arrangement like this one, what this person, who is actually positioned within the cabin over here, is going to do is that they will give theta r. They will, provide the value for the reference or command input, which is theta r, depending on where they think the target is present. So here now, this system is, you can see that the dish is over here. The person is controlling from there. Naturally, it is going to be a remote sort of arrangement, right? So now, I'll come to the application a bit, in a bit more of details after we do the derivation of the your model of the system, where you are going to understand it a bit better, I believe. So here now, coming to the remote position control system. So here now, first of all, we come to this unit, which is the potentiometric error detector. So what is the output of the potentiometric error detector? It is epsilon. So we are writing all the equations in the Laplace domain. So you can see this first equation over here, which is epsilon s, that is the output of the potentiometric error detector, is proportional to the difference between theta r and theta c, and the constant of proportionality being Ke. So epsilon s is equal to constant Ke multiplied by theta rs minus theta cs, right? So this equation actually describes the entire model for this portion, that is the potentiometric error detector unit, right? So that equation has been written down over here, this one, the first one that you see. Okay, gear ratio is taken as N1 is to N2, that is mentioned over here first, right? So next we come to the amplifier unit, which is this one. So as far as the amplifier is concerned, the output of the amplifier is VA, right? Input of the amplifier is epsilon. So the equation of the amplifier unit is given by VAS is equal to the amplifier gain multiplied by the input of the amplifier, which is epsilon s. So this equation VAS is equal to KA into epsilon S actually describes the entire dynamics of this amplified unit, right? That is taken care of. Next, what we have is we have the servo motor over here, right? So now, as far as the servo motor is concerned, we find that in this unit, this is in this remote position control system, there is the servo motor and the servo motor shaft is actually coupled to the load. So here, basically, when we take the model for the servo motor, we are going to use the same model that we had derived for the armature control DC servo motor just in the previous class. We are going to apply that model. But the only thing is that when we when we take into consideration the moment of inertia and the viscous friction coefficient, we have to actually, use the entire, meaning the overall moment of inertia of the motor and the load unit combined. Similarly, the viscous friction coefficient of the motor as well as the load unit combined have to be taken when we write the equation that is equation of the transfer function. So basically what I mean to say is that we have already written the equation for the error detector and also for the amplifier unit. Now we have come to the servo motor. Now when we write the transfer function of the servo motor, we are going to, it is in the armature control mode that we can see from here. So we are going to use the transfer function for the armature control DC servo motor. The only difference is that over here, the shaft of the motor is coupled to the load. So basically, the overall moment of inertia as well as the overall viscous friction coefficient has to be taken when we are writing the transfer function instead of only the motor moment of inertia and the motor viscous friction coefficient that we actually took into consideration when we had only the motor unit. Over there, when we had studied the DC servo motor, we had not considered whether it is coupled to the load or all that. So basically, only JM and FM were considered. But over here now, we have to consider the overall J and the overall F. I hope that is clear. So now, in order to find the overall J, we actually would have to find out the equivalent moment of inertia J when reflected on the motor side and the overall viscous friction coefficient when reflected on the motor side. Okay, so for that now you are familiar with such expressions. The J, that is the overall moment of inertia or the equivalent moment of inertia, if I call it, is equal to Jm plus the gear ratio square JL, right? So it is Jm plus N square JL, where we say that the gear ratio is N is to 1, right? So that will amount to Jm plus N1 by N2 whole square into JL, right? Similarly, F, that is the equivalent viscous friction coefficient, is equal to Fm plus N square FL. So, we have already got J and F. Now we can actually write the transfer function, that is the model for this particular unit. So as far as this unit is concerned, you would be correct that the output of the motor is basically the angular position of the motor, input being the armature voltage or voltage applied at the armature. So theta M S by VAS, that is going to give us the transfer function, which is equal to, it's the same transfer function that we had earlier derived for the DC servo motor in the armature control mode. As I told you, only difference is that J and F are calculated as the equivalent J and F instead of only the motor one. So theta ms by Vs is equal to Ki by S into Js plus F whole into Ra plus Sla plus Kb Kis. Derivation has been done earlier, right? So this is written in the time constant form and happens to be like this, right? Just taking out Ra and F common and then writing in the time constant form in the form of tau m, where tau m is given by J by F and tau A is given by La by Ra. And now, we also know that La, that is the inductance of the armature, is negligible. So in case La is negligible, your tau A is negligible. So tau A is approximately equal to 0. So this is going to give us the the transfer function of the motor unit, this servo motor unit. Okay, so now, I mean, neglecting tau A, this is what we have, isn't it? I mean, I'll just go to the previous slide here. Tau A is negligible, so here we will be left with Ki by, now you can see RAFS whole into 1 plus S tau M plus KB KIS, right? So that is, I mean, taking S common, that boils down to Ki by RAF into 1 plus S tau M plus KBKI whole into S, right? So this is the overall transfer function of the DC servo motor in the armature controlled mode, which is present over here, provided the armature inductance is negligible, which is, I mean, practically going to be the case. So now over here, we try to just, I mean, take terms of the same order together. So the second order term is written first. So S square into RA into F into tau M, which is J by F. So that's the second order term. You can see this one multiplied by that and then the S. And then collecting the first order terms. So there are two first order terms, one coming from RAF into S and the second one KBKI S. So I mean, they are collected together over here. So that overall now, this is the transfer function after doing that. I mean, after we arrange and write. Now, if we divide the numerator and denominator by this, that is this particular term over here, that's RAF plus KBKI. Why we are doing that also will become evident in a moment. So if we divide the numerator and denominator by RAF plus KBKI, we have in the numerator KI by RAF plus KBKI. In the denominator, we have the first, I mean, S square into this, that is the first term becomes this into S square, plus in the second term, you have S into this is 1, right? So that now, if we, I mean, try to simplify matters a bit, the numerator you can see is Ki by RAF plus KB Ki. So all of these are constants. Ki is a constant, Ra is the armature resistance, it's a constant. F is the viscous friction coefficient, which is a constant. Kb is a constant, that is back EMF constant. Ki also is a constant. So in the numerator, we have, I mean, if we calculate that, it will amount to a simple constant, which is denoted as Km and is called the motor constant, motor gain constant, given by Ki by RAF plus Kb Ki, right? So that is the entire numerator denoted by Km, which is motor gain constant. In the denominator, we have S square into a constant, right? So that constant is actually denoted as tau m prime, and it is called the motor time constant, given by, you can see, Raj by RAF plus KBKI, which is this one, right? So this first term becomes S square into tau m prime plus this is S, right? So if we take out S, we have in the denominator S into tau m dash S plus 1. So the entire DC servo motor, armature controlled mode servo motor boils down to, the model boils down to this, that is theta ms by VAS is equal to some constant Km by S into tau m prime S plus 1, right? Tau m is the motor time constant, right? So this is the model of this portion of the remote position control system, right? We just try to simplify matters a bit so that we are able to obtain the entire model, I mean, in a sort of compact fashion, and we are able to apply it if necessary. Apply means we will be able to use the model of the remote position control system wherever necessary. So now from there, okay, so let me just go to the previous slide here. Okay, so here we have got tau m by VA. What is sorry, it's a slip of tongue. Theta m by VA. What is theta m? theta m is the angular position of the motor shaft, right? But what we require is basically, if we want to complete this overall model, what we would be requiring is that here on this side we had theta r and theta c, and then epsilon, and then we have the model of this portion as well, and the model of this portion. Now to complete the overall system, this dotted line that is shown as the feedback has also to be taken into account. Now we see that theta L is actually coupled to theta C, whereas now, theta L and theta M are not the same. So here now we have to, find the relation between theta M and theta L, and then accordingly we would be able to complete the overall block diagram. So theta M by VA is given by this. Now, if we were to find out theta L by VA, then we would have to take the appropriate gear ratio, isn't it? So motor transfer function including load now is written. So including load means theta L by VA is what we want. Instead of, okay, so let me come to the block diagram which is already drawn over here so that it's easier to understand. Okay, so in the block diagram we find, okay, theta R is the reference input, theta C is coming as the feedback signal from the load. We'll come to that. So it's a negative feedback. Excuse me. Now, the output of the potentiometric error detector was denoted as epsilon s. So epsilon s is equal to Ke into theta r minus theta c. Intermediate signal is denoted as Es, the error between theta r and theta c. But nevertheless, as far as epsilon is concerned, epsilon is equal to Ke into theta r minus theta c, which is what we had derived for the model of the error detector. Now, coming to the amplifier, if you recollect, the amplifier was the equation or transfer function for the amplifier was VA is equal to Ka into epsilon, or VAS by epsilon s is equal to Ka. So that is represented over here. Now, armature voltage VA we have already got. So theta ms by VAS we had derived on the previous slide, and that's given by Km by S into tau m dash s plus 1, right? So now what we want to do is, here we have got the feedback as theta C. I've also said that theta C is equal to theta L, which is the angular position of the load. So if we want to find the, missing link between the load angular position and the motor angular position, missing link comes from the gear ratio, that is N1 by N2. So that is what has been drawn over here. That is basically this block, which is going to give you the conversion factor between theta n and theta L. So that now if you want theta L by VA, that can be got from theta m by VA into theta L by theta m. You can see, theta m has been taken in the numerator and denominator as extra, terms. Now, why this has been done is that we would be reusing the theta m by VA transfer function which we've already derived, and also we would be using the ratio, that is the gear ratio between theta L and theta m. So that now the first portion, that is theta m by VA, is given by Km by S into tau m dash s plus 1, right? And theta L by theta m is the gear ratio, which is N1 by N2, right? So once that is done, we have got the ratio between, or rather the transfer function between theta L and VA. So the transfer function from theta L to VA is given by this, okay, which is what we have got also in the block diagram. Now, the open loop transfer function from this block diagram. So, on the basis of all that, we've already drawn the block diagram. So, what is the open loop transfer function? Over here, the open loop transfer function is, you can see from, this is theta L, that is the last point of the forward path, and the forward path is starting from here, that is from the error point, right? So theta L by ES is going to give us the entire forward path transfer function, right? What is the entire forward path transfer function? We see it's equal to Ke into Ka into Km by S into tau dash S plus 1 into the gear ratio, which is N1 by N2. So that actually is denoted as GS, which is the forward path transfer function between ES and theta LS, right? So that is the forward path transfer function written for you, right? Now, if steady state, sorry, uh, let me restate that. Now, if you recollect, I had stated that this system, that is the remote position control system, is actually used to track a target. Track a target means the orientation of the dish should be such that it is pointing towards a target. So that would mean that the difference between the load shaft and the reference shaft should be equal to zero, at least in the steady state. So it implies that here now, if I look at the block diagram, this, that is theta r is the reference command and theta l is the load shaft angular position. So basically, the overall objective of such a system would be to obtain a zero steady state error. What do I mean by zero steady state error? When I have zero steady state error, it would mean that theta L will be directly following or closely following the reference command, that is theta R. So for that now, what we are going to do is we are going to analyze the overall system model that we got already in the form of the block diagram over here, as well as in the derivation with the forward path and the feedback path. Feedback path, of course, you can see is a unity gain, right? I already mentioned that since there is no gearing arrangement between the load and the, this theta C, that's the shaft of the error detector, basically the gain over here in the feedback path is equal to 1. If there would have been a gearing arrangement which was, which had a non-unity gain, that gain would have come in the feedback path, right, over here. But nevertheless, for our arrangement as we are studying it, this is equal to a unity feedback, right? So now we are going to study what happens when a step input theta r is applied to the system. So the input signal is theta rs. Now, if a step input is applied as theta rs, basically we are denoting the amplitude of that step angular, position. Um, uh, the amplitude is given by capital theta. This notation that you see, which is appearing like a smiley sort of thing, is actually a capital theta. So capital theta is the amplitude of the step that we are applying. Naturally, when we take the Laplace transform of the step input, it is going to be capital theta by S. So this is the input that is being applied, right? Now, if we want to find what the steady state error is going to be for this particular system that we have. So how do we find the steady state error? We already have the forward path transfer function given by G, this GS, which is something that is derived over here, right? So the forward path transfer function is GS. The feedback path transfer function is what? It is a unity gain 1. It's a negative unity gain feedback. So what would be, how would we find the steady state error? Steady state error can be found by taking limit of SES as S tends to 0. You can also directly, find what the type of the system is and apply accordingly. Because we are applying a step input, it's going to be standard. You can try it that way as well. Here we are doing it from scratch, that is from the basics again. So here, what we would have to do for finding the steady state error is that we would have to take limit of SES as S tends to 0, where ES is given by the error signal, that is this one, right? So the error signal is, how do you get it? It is going to be equal to the error transfer function multiplied by the input, right? So the error transfer function is how much? It's going to be your 1 by 1 plus GS, right? Where GS is the forward path transfer function. I hope you can understand what I'm saying. If not, please let me know, because since you cannot see me, just hear my voice, maybe a bit difficult to follow at times. Also, there may be some slips of tongue that I have at times, but I hope, that's not happening. So I hope you can see the cursor as well. So basically, the error signal if it is ES, so limit of SES as S tends to 0 has to be taken. How do we get ES? ES by RS is equal to basically 1 by 1 plus GS that we had done earlier when we were doing the steady state error. So ES is going to be equal to what? It's going to be RS by 1 plus GS. Now, when I say RS, I actually mean the reference input, the previous notation that we were using. So in this case now, the reference signal is given by, since it's a step, it's given by theta by S. So S into the reference input signal, which is theta by S, by 1 plus GS, which is GS is written over there. So that is effectively the steady state error signal, right? So now if that is your calculated, you see this S is over there. So you would have to, sort of multiply numerator and denominator with that. Otherwise, you will not be able to actually calculate because going to be. Now, just verify this. Are you getting this is equal to this limit as S tends to 0 is equal to 0? Can you verify that and tell me whether it's okay?
Yes, ma'am.
Okay. So basically, because of this S over here, you multiply numerator and denominator with S. So here you get a constant, that S vanishes. In the numerator, you have got an additional S. So when S tends to 0, the overall, this limit is going to be equal to, when calculated, this is going to be equal to 0. So that basically what we have got is that the steady state error of this system to a step input is going to be equal to 0. Alternatively, we could have also seen the type of the system. You can see that it's a type 1 system and also a step input is being applied. So you calculate your position error constant, and then accordingly, what is going to be the position error constant in this case? Let us say the type 1 system, you can see this 1 by S is there in your forward path transfer function. What is the position error constant for this? How do you get the position error constant, by the way? What happened? How do you calculate the position error constant for this? Given the forward path transfer function, GS, and the feedback is a unity feedback. So what is the position error constant? What happened? Limit of GS as S tends to 0, isn't it? So limit of GS as S tends to 0 over here, how much will it be? You can see GS. What happened? How much will be the position error constant? My goodness. Okay, so limit of GS as S tends to 0 over here, you can see is going to be equal to infinity, and your error, steady state error will be 1 by 1 plus Kp, which is going to be equal to 0. So either way, if you calculate by using the error constant method, or that is that method directly, or you go from the basics by just applying your final value theorem. Either way, you are going to get the same value. That is, the steady state error is equal to 0. So if the steady state error is equal to 0, what does it imply? It implies that the difference in between the output angular orientation and the command signal, that is the reference input, reference shaft angular position. The difference in between the two is going to be equal to 0 in a steady state. So there may be transients, and then ultimately it's going to be settling down to the same value. That is, the output shaft is going to closely follow the input shaft, right? So we will do another thing before closing down today. I think I have about 10 minutes or so. Okay. So here now, I mean, what has been done is that, I mean, next what we would like to do is we would like to study the effect of load or disturbance torque. So this particular system, that is the remote position control system, as I told you, is used to, used to control the angular position of the dish and make it point towards a particular target, right? So now, if let us say that there is a fixed target somewhere and the dish has been oriented in that direction already, right? Now, let us say that there is some disturbance in the form of maybe a storm which is taking place, or a strong wind, which has somehow disoriented the angular position of the shaft of the antenna. So, what will happen? Basically, the position, angular orientation of the dish, which was earlier pointing towards the target, will no longer be pointing towards the target. But now, I mean, what will be the effect? On the overall system. So that is what we are going to study right now. So for that now, coming back to the block diagram of this system that we've already derived, here the block diagram, in the block diagram rather, this particular block, that is the servo motor block, has been broken up into two parts. You can see how it has been done. It's done in a slightly different fashion meaning that another notation has been used over here, that is suffix capital M, capital K suffix capital M, which is given by K small m F equivalent. That is basically the product of these two. Now, this has actually been done because you will see that whenever, we want to study the effect of the disturbance, basically the disturbance is going to produce a torque. So, we are actually going to study the disturbance torque. So, unless and until in the block diagram we get hold of the motor torque and we try to actually find out the equivalent motor torque which is being produced, and then we can study how that is being affected by the disturbance torque. That can that is the approach that we would be adopting. Now, in the previous block diagram that we had drawn, we have theta m, that is the angular orientation of the motor shaft, and we have VA as the input signal. But if we were to study the effect of the torque, it's difficult to study directly from this block over here, because the torque is no longer, it's not explicitly visible, you can say. Okay, torque of course is being produced, but as far as the block is concerned, the block internally takes care of the torque which is being produced. Here, this block has been broken up such that we are able to see how much the torque is going to be, and then consider the effect of the disturbance torque. So that is why this has been done over here, where now you can see this block, that is Kn, is actually the transformation ratio between the torque which is being produced and the armature voltage which is being applied. And then you have this block giving you the relation between the motor angular position, that is theta m, and the motor torque. So of course theta m and tau m are Tm are related by this. We are already aware of this, where J equivalent and F equivalent are the equivalent moment of inertia and viscous friction coefficient respectively, right? So that basically tau m dash is equal to J equivalent by F equivalent, that we already knew. Here we are using EQ as the suffix. That's the only difference. Okay, we already took J and F. It's the same thing that we are mentioning, but just to sort of make matters obvious, the notation has been used as F equivalent and J equivalent over here. So tau m prime is equal to J equivalent by F equivalent. Km, K suffix capital M, is constant which is being introduced over here, which is known as the motor torque constant, and it actually gives the relation between the torque produced in the motor and the VA. Now, I mean, comparing between these two blocks, you can see Km, capital M, is equal to K small m into F equivalent, because I mean, over here we had tau m prime. Now tau m prime is derived as J equivalent by F equivalent, and then multiply numerator and denominator by F equivalent. We are going to come to this one. In the numerator, there would have been an F equivalent, which actually has been considered along with this Km, right? So that is why Km, which is the motor torque constant, is given by K suffix m, a small m, I mean, into F equivalent. So that now, I mean, we have the original block that we had, Km by S into tau m dash S plus 1, is written over here. The breaking down has been shown, as I told you. So tau m dash has been replaced by J equivalent by F equivalent, then multiplying the numerator and denominator by F equivalent. This is what we get. And then substituting Km into F equivalent as K suffix capital M, which is the motor torque constant, and then I mean expressing in this form, so that we get two separate blocks. One is giving the torque constant only, so the output of that block will be only the torque, and then this block with the output of which is going to give you the angular position, that is theta m. Now this has been done, I mean this breaking up has been done keeping a particular thing in mind. As I told you, since we have to consider the effect of the disturbance torque, that is why it would be, I mean, essential to find what the torque produced by the motor is, and that is why this has been explicitly shown over here. The equivalent units are shown. Units you can just see from this slide, which is already given to you. Now, coming to the modified block diagram, where now the disturbance or the load torque has been shown. So TL is coming with a negative sign over here to show that it is going to be, I mean, acting in a direction such that this Tm is the motor torque produced, right? So, I mean, here in the previous diagram, we had seen that VA into Km is equal to Tm, that is the torque produced by the motor. And the torque produced by the motor, when transformed via this block, is going to give the angular orientation of the motor. Now, considering the effect of load or disturbance torque, that is minus TL, which is shown over here in this, I mean, summer, at this summing point, and is going to be, I mean, giving and having an effect which is going to oppose the motor torque which is being produced. That is why the negative sign is shown over here, right? So now from this block diagram, the rest of the block diagram remains the same. Only thing is that we tried to put in show the disturbance torque, and in order to do that, we had to, I mean, show how it is opposing the motor torque. That is why this breakup of this overall motor unit block diagram has been done. So now coming to the derivation again. Okay, so derivation, this is the error detector equation, which is written as, it's the same as what we had earlier. The amplifier VAS is equal to K into epsilon S, which is also the same, so that VAS is equal to, we substitute from the previous one, it's going to be this. Now the torque developed is going to be considered. So Tm, that is this one, is equal to K capital M into K capital M into VA. So that now Tm is equal to Km into VAS. So VAS we have already got from here, that is substituted over here, right? So that now if we look at this expression, we find Km is a constant, K is a constant, and Ke is a constant. Overall, K, Ke, and Km together are taken as another constant, capital K. Appropriate units, of course, have to be considered. So, I mean, the unit of Ke and the unit of Ka and the unit of Km multiplied together will give us this, that is Newton meter per radian. You can verify that and see. So, basically, it boils down to Tm, that is the, motor torque, being equal to some constant into theta r minus theta c. That constant being given by Km, Ka, Ke in Newton meter per radian, right? So, I mean, this you can verify also. So, motor torque constant is in Newton meter per volt. Your Ka is in volts per volt, right? And then Ke is in volts per radian. So, overall, basically, it's going to be Newton meter per radian. You can just, I mean, see that yourself as well. So that now what we will be doing is we are going to, make a simplifying assumption over here. The simplifying assumption being that for this analysis, the rest of the analysis, what we are, assuming is that this gear ratio we are saying is equal to unity. If it's non-unity, again, you have to, take this N1 by N2 in the appropriate places. But for the time being, we are assuming that there is no gear reduction between the output shaft to, and the your between the output shaft to the load, and also the output shaft to the feedback port. This already was equal to unity, as I told you. Theta C is equal to theta L, that earlier we had stated. Now we've put that theta C over here because that is anyway equal to theta L. We are also now making another simplifying assumption, that is we are assuming that the theta C is equal to theta M, that is this gear ratio is also equal to unity. This is, of course, without loss of generality. In case we have a non-unity gear ratio, theta C will be equal to that gear ratio into theta M. That has to be taken into consideration. For the time being, we are assuming that theta M is equal to theta L is equal to theta C. So from there, I'll just take another 3 or 4 minutes or so and then take the attendance in case you have a class also. Because I want to finish off this portion today at least. So now, when the load or disturbance torque is acting on the motor, the torque produced by the motor will be having to, balance all the opposing torques, and that would be, equal to the sum of the opposing torques. So that now, Tm, we already said on the previous slide, if you recollect, Tm is equal to K into theta R minus theta C. That has been applied over here on the left hand side. On the right hand side, what do we have? On the right hand side, we have the sum of the opposing torques. Now, what are the opposing torques? First of all, TL is one of them. Also, we have this signal over here. This signal is what? Theta M by this signal is equal to J equivalent S square plus F equivalent S, such that this signal over here is also a torque, naturally, for the units to match over here. So that torque is given by J equivalent S square theta CS plus F equivalent S theta CS, right? So that this is what we get. Now from there, just collecting terms containing theta CS and taking them to the right hand side, rest of the terms coming to the left hand side, this is what we get, right? In case you are unable to understand, nothing, that you shouldn't be able to understand. It's very simple. But anyway, it just interrupt me. Okay. So basically, this is what we get. Now, in order to find the steady state analysis, but before that, in order to find the output expression in terms of the inputs to the system. Now, as far as I'm again showing the previous slide, what is the output of the system? Theta C, right? What are the inputs to the system? We have the reference shaft position, that is theta R. We also have the disturbance torque, which is another input to the system. The system does not know that this is not desirable, that is desirable, and all that, right? So for the system, as far as the system is concerned, both the disturbance torque as well as the reference input are the inputs. So that now, we are expressing theta C in terms of both theta R and theta and TL. So that in order to do that, we are going to divide the right hand side and the left hand side by this coefficient of this theta CS. So that is what you see on the next slide. So theta CS is equal to K theta RS by J equivalent S square plus F equivalent S plus K minus TLS by J equivalent S square plus F equivalent S plus K. So theta CS is given by this. So you can see that the output is dependent both on the reference input, which is theta R, as well as the disturbance input, which is TL, right? So now what we are going to do is we are going to do a steady state analysis, very simple one, assuming both the signals, the input signals are steps. So as far as the input signals are concerned, what I mean is that the command or the reference input theta R is given by a step with magnitude capital theta. Again, the same symbol has been used. And the load or the disturbance torque is denoted by T capital L. I mean, you can see it's without the italics. So the variable that was used earlier was with italics, but the constant value TL of the load magnitude, I wish I could have used a different notation, but anyway, you can see. It's the constant is denoted with the vertical notation without the italics, right? So that now TLS is equal to capital TL by S and theta RS is equal to capital theta by S. So both theta R and TL are considered as step inputs. So that now if we, see what theta CS is by applying these inputs, this is what we get, right? So now in order to find the steady state output, the steady state output will be what? Limit of S theta Cs as S tends to 0. Not the error, we are looking at the steady state output over here, right? So steady state output is given as limit S theta S as S tends to 0. So if we do that, this is what we get, and you can see that S and S in the numerator and denominator will be cancelling out for the first term. So that we will be left with what? We have K theta in the numerator and denominator we have S at 0. So K. So it will be boiling down to only theta, capital theta for the first one when we take the limit. Similarly, the second one, we have the minus sign over there, TL, and now the S and the S over there cancel out. In the denominator, we have this is multiplied by 0, this is multiplied by 0. We have the K as the constant. So overall, from this second term, we get TL by K. So that the steady state output will boil down to capital theta minus TL by K, right? So that now there are certain things that we can see from this. That is, when TL is equal to 0, then there exists an exact correspondence between the input and the output. Input being capital theta because that is the step that we have applied. Output will also be equal to capital theta in the steady state if there is no load torque. So that there will be exact correspondence between the output and the input, and the system will perform the task of tracking the output. On the other hand, if there exists a non-zero value of the disturbance torque, in that case, you can see that the output will no longer be equal to only theta, but it will be something different. It will be lesser than theta, lesser by an amount which is proportional to the torque, that is the disturbance torque, and inversely proportional to the gain K, right? So if somebody asks you that, okay, I have a load torque, I cannot do anything about it. Now, how can you give me a suggestion regarding how I would be able to make my tracking better? To make my tracking better means what? Making the correspondence between your input and output, precise. So correspondence being precise means what? The output should be as close to capital theta as possible. So in order to do that, what would be necessary? We would have to make the second term as small as possible, right? So in order to make the second term as small as possible, what we can do is we cannot do anything about the load torque, but we can try to design a system such that this constant gain is large or as large as we can make it, considering other things also. So if we can make K large, what would happen? This term would become small so that we can reduce the effect of the load torque by increasing the gain K. However, of course, I would have to mention over here that things are not that rosy, meaning that it is, increase in the gain K, the value of the gain K, if it is increased, there are lots of other things that are at peril, meaning that basically you would study in the other part that when if you are doing root locus technique or any stability analysis methods, you would be seeing that increasing the gain K, even the Bode plot and all that, you would be seeing that increasing the gain K essentially would reduce the stability of the system, making it more oscillatory, etc., etc. Right? So it is not, a black and white matter, meaning that, okay, fine, I want to reduce the error, so I want to reduce this, second term, so I make K as large as possible. You will not be able to make K as large as possible, right? But of course, you can increase it to a certain extent without, hampering the steady state performance. So without hampering your transient performance, meaning, as far as the oscillations in the transients are concerned, you would have to also have a look at that. So often what would be done is a trade-off would, There is a term which we use for such things known as trade-off, TRADEOFF. It means that basically you have to keep in mind how much of steady state error you can withstand, you want to, keep in your system, at the same time, not compromising the stability of the system. So you will be able to increase the gain K, but only to a limited extent to get a smaller steady state error, but you cannot actually, try to make this gain K very large so that this becomes equal to zero. That is from the point of view of the design, as as far as that is, when a design is done, that has to be kept in mind. But apart from that, from the point of view of steady state analysis, obviously you can see that it is desirable that the gain K is made as large as possible so that a correspondence between the input and the output is possible, and the system will track better in the presence of load or disturbance as well. So that's all for this particular class. I'll stop the recording. I'll take your attendances. Please don't leave before giving your attendances.